Hello everyone, welcome to OdinSchool. In this class, we are going to learn about one of the most widely used metric in statistics in terms of hypothesis testing, which is ANOVA. ANOVA is a product of F test. We will see what is ANOVA, and then we will see what are the different types of tests that we can use in ANOVA, why we should use ANOVA, and what are the use cases and all those other things in this particular class. Before we get started into the class, let's first have the understanding of why should someone learn statistics. Statistics is one of the most widely used subject in both professional as well as in personal life. Talking about statistics, every day we make small decisions and big decisions. If I wanted to buy a house, I have to see what is the bank loan, what are the bank loan possibilities that I will have, and what is the down payment amount that I need to have in my hand. What will be my registration fees, and what will be the other relevant numbers that I should know in order to purchase a particular apartment. Now, this is a decision that actually is huge in numbers. So even in this case, you have to use statistics. Even if it is a small number, should I buy a product of from a particular brand A or a particular brand B? What is the cost difference between them? What are the reviews that actually stands out between product A and product B? Whether if I buy this product A, how will I? How many days can I use this product A? How many days I can use this product B? So for every small action that we do in real life, as well as in business, we always rely upon numbers, quantitative understanding towards the output. So statistics help us to quantify the decisions that we make. It also backs us our decision and saying that, see, you don't have to depend on your gut feeling or basic intuition. You can also rely upon numbers to generate and understand what will be the output. The same happens with business also. If I wanted to identify what is the area in which I need improvement in my business, I need to analyze it with the help of statistical measures. If I wanted to know what is the area that is performing good, what is the area that I should reward. Even promotions in organizations are calculated by 3 sigma rule only, which is again a statistical, simple statistical measure. People who are falling under one standard deviation, people who are falling under two standard deviation, and three standard deviation. Basis that your promotion varies, promotion or your hike varies. So basically, statistics is simply nothing but a subject which is used irrespective of your professional life or personal life. In both the places, we rely upon numbers a lot to generate a number, to generate an output out of a quantitative input. We all need statistical measures. Now let me quickly introduce about OdinSchool as well as about me. OdinSchool is a technology upskilling platform. They help us continuously acquire new skills. Their motto is to stay skilled and stay ahead. About me, I'm Gautam Kumar Jayachandran. I have 6+ years of experience as a data scientist. I worked with several technologies, Excel, SQL, Python, Tableau, Power BI, machine learning, and analytics. My current domain is finance. With that said, let's quickly jump into today's agenda and see what are we going to learn. Today we are going to learn about ANOVA completely. What is ANOVA and what are the different types of it? One-way ANOVA and two-way ANOVA. How are they different from each other? And then we will also see there are two types in two-way ANOVA itself, with replication and without replication. We are going to see that also with an example completely. First, let's understand what is ANOVA theoretically. The complete ANOVA is basically an abbreviation. The full form of ANOVA is basically analysis of variance. That is what ANOVA is all about. Now, in hypothesis, what is the general understanding in hypothesis? It is about when I have an existing belief. If I have to change my existing belief, I need to conduct an experiment and to prove that what I believe in the past or what I believe in my present is wrong. There is something new to the existing belief. Say, for an example, I believe that India is number one in test rankings, test cricket rankings. But it has to be validated. I can say anything. You can also say anything. Anyone can say any statement. But how do I validate it? If I have to validate it, I will, try to put that statement into some sort of quantifiable experiments and generate an output and validate whether the statement is right or wrong. That is what hypothesis testing does. In business also, if someone is coming and saying, see, I've predicted that your business is going to generate $2 million next month, you can be happy as a business owner, but you need to know how. how do you say why I'm going to generate 2 million sales? Then we have to conduct several experiments and finally validate the statement given by someone else. So that is all about hypothesis testing. ANOVA is a part of hypothesis testing only. Now in hypothesis testing, there are several tests: Z test, T test, and F test. Chi-square test is also there. We have seen chi-square test yesterday. We are seeing ANOVA today. Tomorrow we will be learning about in the next class we will be learning about t-test and z-test. So it will cover the entire statistical tests that can be performed in hypothesis testing. With that said, let's quickly get into what is variance first, and then from there let's see how the ANOVA is going to help us understand whether there is statistical significance between the given groups. So I'll explain them with easy examples rather than confusing you with a lot of theories. Variance. First, let's understand what is variance. Variance is simply nothing but a statistical measure which will tell you how wide the data is spread from the middle of your data set. When I say middle, basically your mean value is the middle of your data set. From the mean value, how widely do the data data are what I would say are spread. If the data is spread extensively away from the mean value, it is a skewed information or a biased information. So basically, let me show you with paintings. Okay, this time we just close this. In the meanwhile, I'll show you the pictures of it. So bias, variance, trade-off. I'll just take the bullseye example. Bullseye example is better used to understand how the data is distributed. Exactly. Look at this. So if you take bullseye example, variance is all about, in this case, we have very less variance. For high variance, if you see from the center, how far the data is distributed. Now let me show them with an example in my whiteboard. This is the mean value. So this is the data set distribution, and I'm just going to have a mean value. Oops, doesn't look center. Yeah, now this is my mean value. Now how wide the data is distributed from the mean value is what variance is all about. It can be calculated with the help of standard deviation or by squaring the differences as well. Now let me show you the data points here. And wide it will not be just like bias where the data points will be present only at one end or one side. Here it will be spread far away from your mean value, and it will be widespread as well. It will not be spread in only one portion of the data set. It will be spread almost in all the places of your data set. Your data set, the data set in real time has really good chance of being widely spread from data or being spread in only one position, causing bias in it, basically noise in the data set. So in this case, looks like the data set is the data points in the data set have lot of variance in this. When you have a lot of variance in the data set, the problem is the output will also be varying far away from the mean value. Now, why do I need to understand why and how the data is distributed from the mean value, and how is it going to help me achieve or understand the difference between two groups? Yeah, from the mean value, how wide the data is distributed, and learning this, how is it going to help me understand the difference between two groups. Now the idea behind ANOVA is very simple. We are going to compare two or more than two groups. For two groups we will use t-test and z-test. ANOVA is used explicitly for groups greater than two. When I have three groups and I have to compare between the mean value of three groups and say what is the whether these groups are statistically significant. When I say significant, different between each other or not. So what we will generally do, what ANOVA generally does is it calculates the variance within the group, within one group. So basically if this is one first category and I have second category and I have third category separately, it first calculates the variance within the group, then calculates the variance among groups. how varying the data points are from group 1 to group 2, group 2 to group 3. If the variance is too high, it means that they are different from each other. If the variance is too less, then it means they are not varying very much with each other. They are not differing to each other. They are very similar in nature. This is the idea behind ANOVA. It calculates both within groups and between groups. Within groups, it calculates from the mean value, calculates variance, and it calculates the variance with the overall group value with the mean value as well as a mean value of another group, group 2, group 3, and as well, and identifies whether they are differing in terms of values or not. If there is more variance, it means the data is widespread from the mean value. That is the understanding. Let me first show you how to calculate variance in Excel, then we will see ANOVA with examples. I have taken some example, but before that, let me show you how to calculate variance. Now let's create a data. Students marks. I'm just going to create students with alphabets. I'm just formatting it. I'm zooming in. Now we have students and we have marks. Let me put this in the same format that we usually follow. I'll just keep the text in white and keep the background in a darker color so it will look good. Okay, these are the students and we are going to create marks for each and every students. I'm going to randomly generate the marks. It should be minimum 35 to 100 also. It can be there. 35 being the least mark for passing and 100 being the maximum mark that they can score in the exam. Now we have this value. Now let me plot this data and then show you how the data looks like. Then I'll explain you variance with the help of chart. All right, cool. So we have this distribution. This is scatter plot explaining the values. Now we do not know the mean value. Mean value as in the average marks scored by all the classes, all the students. The average is 73.3. Now let me close this. Then plot 73.3 should be somewhere here. This is my mean value. Okay, once we have this mean value, look at this, the number of data points that are present below the mean value: 1 2 3 4 5 6 7 8 9, the 7 below, and 1 2 3 4 5 6 7 8 8 above, which is very close to equally balanced. Looks like the data is distributed from the mean value equally between both the ends, from the left side of the mean as well from the left side is below. I'll just write it as well. This is actually from the mean value. This is below and this is above. Just write it so you'll be remembering it. So this is below or left side below mean. This is above or right from the mean. Okay, this is the data distribution. Now talking about the understanding of data points here, variance here, looks like from the mean, the data points are not far away distributed. Okay, they are very close to the mean value only. They are not distributed in a very far region. So it looks like the variance in this data set will be very less. There is no level of variance that we can consider, range of variance. Say for an example, if you take range of correlation, it is always plus or minus 1. So we will say if it is plus 1, it is 100% correlated. If it is minus 1, we will say 100% negatively correlated. But you cannot quantify any range if it is variance. It means that if you have a positive value and if you have a very larger value, it means that your distribution is the way the data set that is inside your distribution is far away distributed from the mean value. But look at this, our mean value is 73 and most of the data points are around 70 only. There are very few data points that are far below 70. Look at this, I think this is 40 and looks like 45 50 something, and far away we have 200s as well. So it evens out the distribution in terms of variance. Let me calculate the variance also. To calculate variance, let me manually do the calculation of variance and explain you how we can do it with the help of functions as well. But this just graph, I'll just minimize this and maybe I'll delete it as well. Okay, so calculating variance is very simple. Variance is denoted by, it is x minus x bar, x minus x bar, the whole square divided by, I'll just keep divided in the below, whole square divided by n. There are two ways of uh, there are two ways in which we can actually calculate this, which is basically calculate the standard deviation and then calculate variance from it, or we can calculate a variance and then calculate standard deviation from it. This is the formula. Yeah, this is the formula. So x minus x bar the whole square divided by n is basically the number of items that are present, number of entities that are present. Let us calculate this manually and I'll validate the same thing with the help of a function also. First let me calculate x minus x bar. X bar is basically the mean value which we have already calculated. So I'm going to take the same thing and then say x minus x bar. What is my x? My mean, my individual data points are x and this is my distribution divided by it. So we have x minus x bar generated through it. Then what we need to have? We need to have x minus x bar the whole square. So what I'll do is, this is basically sum of, I didn't specify this. This is basically sum of x minus x bar the whole square and things. So here what I'll do is I'll simply create a new variable and multiply or power it by 2 to the power of 2. To do it, what I'll do is I'll simply multiply this value with itself. So we have some x minus x bar the whole square. The numerator is basically sum of, I'll also keep denominator. The numerator and denominator we are going to calculate now. Numerator is sum of squared deviation. This is my numerator. What is my denominator? Count of values. How many values are there? There are 15 students. So we have the numerator and denominator. Then we can calculate variance. Here the variance will be numerator divided by denominator, which says 429. To validate this, let me calculate variance with the help of formula which is directly there available. On population only I have done this. So what is my original number? This is my overall number. I want variance for this. Look at this. This is exactly the same number that we have calculated methodology, step by step, but the machine simply gives it to you in one step as well using the formula. Standard deviation is simply nothing but square root of variance. That's it. So these two measures are very important uh, in real life in order to understand the way the data is distributed. Again, standard deviation can also be calculated with the help of machine directly. We don't have to do anything. We can directly say how the data is distributed. The standard deviation is 20. Perfect. Okay. Okay. So you see here the values that we calculated manually is equal to the value that we generated out of the machine as well. So it says from the mean value, the variance is 429. When I say 429, it is plus 429 to minus 429. This is the squared sum of squared deviation. This is not the normal deviation. This is the sum of squared deviation. We can to interpret it, we will always go with variance. So this value is within groups because we have taken this only within this group and then we calculated the variance. What machine will do is in terms of variance, it will calculate the variance within groups and between groups also. Say for an example, have another group here, another group here. It calculates the variance between them also and finally tells you whether they are differing from each other or not. In this case, the dataset is not deviating too much from the mean value. Hence, there is very less variance. I can understand that the variance is very less because the standard deviation score is also 20 only. If I perform three standard deviation, I will be able to understand whether it is small or less, or whether it is falling into three is normal distribution or not. But by experience, I can already tell this is a normally distributed dataset only. We don't even have to validate this because from the mean value, none of the values are far away distributed. Looks like there are no outliers in this data set. So I can confirmly call this a very stable distribution. This is how variance is calculated. Analysis of variance, as I told you, it calculates within groups and between groups also to generate an output out of it. Now with that said, let me not save this. Let's go to the theory portion, finish the theory portion, and we'll perform all different types of ANOVA in Excel. There are two types. One is one-way ANOVA, another one is two-way ANOVA. I think that is the next slide. Okay, ANOVA theoretically, ANOVA analysis of experience, comparing groups to see if there is a difference between them. As I explained between, see here, this is exactly what I was trying to explain. With this, what is there are three groups now: group 1, group 2, and group 3. What is the variance among the group and what is the variance within the group? So within, as in this case, it is inside the distribution. We'll see it will compare the mean within all three groups and gives us the total variance. If the total variance is lesser than the critical value, then we can go ahead and then say we can reject the null hypothesis and accept the alternate hypothesis. Or generally, rather than confusing between critical value and statistic value, we will go with p-value. We will calculate the p-value, and once the p-value is less than my alpha level, then we can go ahead and then say yes, we can reject the null hypothesis. That is also something that we can do. So theoretically, a group of, for example, would be a group of psychiatric patients is trying three different therapies: counseling, medication, and biofeedback, to see which of these therapies differ in the outcome. So if I wanted to see if any of these experiments, if any of these therapies are giving better results than the other, we will conduct a ANOVA test, because there are three groups in this: counseling, medication, and biofeedback. If I had only two groups, I can go with a t-test or a z-test based on the sample number of sample that I have. But in this case, there are three groups. So whenever we have more than two groups and we have to compare the mean of three groups to understand whether they are differing from each other or not, we will go with ANOVA. The next idea of ANOVA is, as I told you, there are two ways of ANOVA in which we can perform it: one-way ANOVA and two-way ANOVA. It is very simple. If I have one independent variable in the data set, it becomes one-way ANOVA. If I have two independent variable, it becomes two-way ANOVA. Now in this case, see, this is groups only. Only one group, only one category are an independent variable, but there are three groups inside them. Say for an example, this is the counseled patients. Yeah, if you see the consult patients, there are three groups of it. One might have went for counseling, another one might have went for biofeedback, another one went for medication or something. In those cases, when I have three groups under only one dimension, the dimension is same. They are patients only. They are patients only. This is basically our independent variable. This is your independent variable. Whereas, if you see here in this data set, let me maximize this. In this data set, we have data at a row level, sorry, at a column level as well as row level. This is at a row level, A, B, 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 C, 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 and all those things. And at a column level also, I have information first year, second year, and third year. So here I have two in dimensions. One is genotype of the seed. Next is growth of each seed in different time periods. So there are two dimensions in this. These two dimensions are called as two independent variables. So whenever I have two independent variables in my data set, then I'll go with two-way ANOVA. If I have only one independent variable, then I'll go with one-way ANOVA. Now to just give an example, here this is time dimension, one independent variable. This is genotype. Okay, so there are only two dimensions in this data set. Whenever I have two dimensions in the data set, they become two independent variables. In those cases, I can go ahead and perform two-way ANOVA on top of it. So it is all about the number of independent variables that is present inside the observation, but the logic does not change at all. So it will still go ahead and perform calculations between the groups and within the groups. Let's see the theoretical definitions. One-way ANOVA is defined as a test that allows one to make comparison between the means of three or more groups of data. We just spoke about this. Talking about two-way ANOVA, a test that allows one to make comparison between the means of three or more groups of data where two independent variables are considered. Whereas in one-way ANOVA, the number of independent variables should be one. In two-way ANOVA, it will be two. Then what is being compared in one-way ANOVA is basically the means of three groups corresponding to one independent variable. Here in two-way ANOVA, we are going to compare groups in both the dimensions. If I have three groups, I will compare the three groups in dimension A as well as dimension B. Then the number of groups that one-way ANOVA can have is three or more. Same thing with two-way ANOVA also. But you should make sure that when you have two dimensions, both these dimensions should have more than three groups. Now, if you see here, in this data set, I have three groups in time dimension. I have more than three groups in genotype dimension also. A, B, C, D, E, F, six groups are there. So you should make sure that you have more than three groups or at least three groups in both the dimensions. Now again, the most important thing when we are performing two ANOVA is that the number of times a group takes a test or an experiment should be equal to the other groups also. If you see here, group A has been observed three times. Group B also should be observed three times only. All the groups will be observed same number of times. It is like making sure giving exams for all the students equal number of times. So the entire class might take the test five times. There will be no exception given to topper students also, as well as to the last bench students. So there will be no exceptions given. Everyone should take the equal number of tests. That way your data set will not be biased as an output out of it. This is the understanding there. Now let's go back to the theory. Theory is done. So let's perform one-way ANOVA, two-way ANOVA and things. First, for performing one-way ANOVA, all we need to do is first go to File, Go to more, choose options, choose the add-ins. Just waiting for the add-ins. You need to enable data analysis tab in your data ribbon. That way only we will be able to perform OneWay ANOVA. I have to just choose go here, where you'll have to choose analysis tool pack. Just give OK to it and then go to data page. Here you will have in data you have data analysis. I've selected the entire data set already. I'm going to choose data analysis. Once I choose data analysis, it will give me the option to perform different types of hypothetical and statistical testings. I am going to choose ANOVA single factor. When I say single factor, it is one way ANOVA. Here, there are two ways in which two-way ANOVA can be performed. Two-way ANOVA with replication, two-way ANOVA without replication. I'll explain both. The first thing is give the input range. This is the data. Okay, and the machine is asking me whether the data is grouped by rows or columns. They are grouped by columns only, so I'm going to leave it as it is. The first row contains labels in it, and what is the level of significance? I want 0.05 as my level of significance, which is basically our margin of error. It calculates the values very swiftly. We don't have to worry about anything else. Now see here, it tells you what is the variance in group 1, variance in group 2 and variance in group 3. Then what it will simply do is it will calculate the variance between groups and within groups. Then it will finally calculate the F value, which is basically the ANOVA value, and this is the critical value generated from the table as well. Then we should make sure that we will always look into p-values condition. What is the condition of p-value? When I'll say if my p-value is less than 0.05, then we will say reject the null hypothesis, or we will say accept null hypothesis. We have not declared null hypothesis or reject null hypothesis. Let me derive hypothesis first. What is null hypothesis in this case? Denoted by H naught. There are three groups. What is the general belief? All groups are same. All the groups are same. The output of treatment, I'll maybe elaborate it. Output of treatment of three treatments are the same. This is my understanding existing belief, which is null hypothesis. What is the alternate hypothesis? Someone said no, no, after conducting experiment someone will have good some therapy will be definitely different from other therapies, but in our case we have to accept null hypothesis, which is saying that all the three treatments are are not varying very much with each other. They are very same. There is actually no statistical significant between all three groups. In alternate hypothesis, I'll say will not be the same. Yeah, this is the alternate hypothesis concept. Now in this case, since our p-value is less than the alpha level, we are going to accept the null hypothesis saying that all the groups are same. Now we can validate this also by our general intuition. See here, look at the average value of all three groups. The average is not varying as much as it can be. 220, 233, 243, they are very close to each other. They are not varying significantly. So hence we can also understand that they are not varying much also. Look at the variance. Even the squared difference is not greater than 9,000 or something. This is the squared difference. If you consider the average, then it is very clear that our groups are not statistically significant from each other. This is one way ANOVA at a column level. Let me do the same thing at a row level and show you how does it work. Let me copy this data set. Copy this. So here what happens when your data is present at a row level, and if I wanted to calculate whether they are statistically different from each other or not. Null hypothesis. My null hypothesis is basically all groups are same. Various. My alternate hypothesis is slightly different. My alternate hypothesis says not all the groups are same. Yep, perfect. So let's calculate this. First, I'm going to go to data, go to data analysis, choose single factor only because only one independent variable is there. I'm going to choose the data from here. I'll choose the data in the row wise and grouped by rows. I have to change the data to be grouped by rows. Labels in the first column, yes it is. And this is my alpha level. My output should be present somewhere here. So we can validate the same things. Look at this. The value that we generated as in the column level is the same and the row level as well. And then look at the average does not change anything. The variance does not vary anything. It is very clear that this data set is not having huge variance. Hence, they are not statistically significant. I'll simply say if my p value is less than 0.05, I'll say groups are not statistically, other which ways we will say they are. I think I've written this upside down, so I'll say if the I'll simply change 0.05. So they are, no, I think I've written this correct only. If it is greater than 0.05, sorry, if it is less than 0.05, then we will say they are actually different from each other. In that case, this is going to be not less than, this should be. So it says groups are not statistically different, which is simply nothing but a statement consolidating or validating our null hypothesis. So in this case, we will accept the null hypothesis and reject the alternate hypothesis. We believe that all the three treatments are equal in terms of generating the same output. There is no much difference between any of the treatments. So we'll have to find out another treatment which will be statistically significant from other groups. So this is the understanding of one-way ANOVA. Let's go on to the two-way ANOVA with replication and without replication. Talking about with replication, it is all about allowing a group or a subgroup to to participate in the experiment multiple times. So basically, replication is nothing but allowing duplicates. If you see this observation in the left side, we have genotypes A taking the test multiple times. A has taken the test multiple times, A 3 times, and same happens with all the other groups also. All the other groups have taken the test 3 times to see if there is a difference between groups or not. But however, in a case without replication, this is allowing with replication. What happens without replication is you will not allow the students to take the test n number of times. Every student will be taking the test only once, but they will be taking different tests, different subjects, maths, physics, and biology. This is without duplication. This is with duplication. This is the difference between two-way ANOVA with replication and without replication. Now let's first define our null hypothesis and other things. Null hypothesis. Null hypothesis in this case will be multiple because we have two dimensions. We have to have two different uh, null belief. The belief is all 3 years the growth was same. This is for my time period dimension. Then the second dimension is all six, I think. Let's validate how many in total are there. Six, perfect. Okay. So the second belief is all six genotypes are genotypes generate same growth to the plant. And what is the third belief? Intersection of both these dimensions. I'll say all 3 years, all six different genotypes did not vary in growth. This is my null hypothesis for two-way ANOVA with replication. So I have two dimensions here. One is genotype, another one is time dimension, and then the intersection of both. So all three will be my existing belief. What is alternate hypothesis? My alternate hypothesis is going to change this. Okay. Yeah, that's it. So in this case, so I'll just change the data set. So all 3 years the growth was different. I'll say all six genotype generates different growth. All 3 years, all six different genotypes vary in growth. This is the alternate hypothesis. Now let's validate which one is true and which one is false. So whenever we have an issue like this, so what we will do is we will always try to perform any type of statistical testing, but based on the number of groups, the test differs. So in this case, it is going to be null hypothesis here. This is alternate hypothesis. That's it. So we have the statements. Okay, will be there. Hmm. Yeah, so let's go ahead and perform two-way ANOVA. To perform two-way ANOVA, I'm just selecting the data, going to data page, going to data analysis, see a two-factor with replication. I'll just give OK, and then the input range will be the entire data set here. Then it is asking me how many rows that are there per sample in the second dimension. In the second dimension, there are three line items, three rows for each and every sample. So I'll give three. What's my alpha level? 0.05 as usual. And then where should be my output? My output should be in the same sheet as this, and then give OK. It generates a ANOVA table for me, ANOVA calculation for me, and gives us the output. So summary information for each and every genotype presented here. Then we can see the overall average in 3 years. Okay, for across all the samples. And what is the sum? Looks like there is not much of a difference, but variance also is very small compared to all these three. But looks like 3 and 5 and 8 might be a huge difference because the values are in decimals, very limited numbers only. Let's validate this. However, let's validate this. We can reject our null hypothesis if our value p value is less than 0.05. If you see in all these three cases, sample at a column at an interaction level. So basically both the interaction, the third point that we speak. So let's write the logic here. If my p value is less than 0.05, then I will say accept null hypothesis, or I'll say reject Null hypothesis. Sorry, I should have written this other way around. It should be if it is greater than 5, we will accept this null hypothesis. Other cases will reject null hypothesis. In this case, in all the three cases, we are rejecting the null hypothesis, which is a good thing. We now know that all the three groups, all the three different years, what is our alternate hypothesis? All 3 years, the growth was different. All six genotypes generate different growth. So one genotype seed has a different level of growth compared to the other one, and all 3 years all six different genotypes vary in growth. But here the only catch in hypothesis testing is that we will not know in which year we had the difference. In 3 years there might be there will be some difference. That is very sure about hypothesis testing. It says there is difference in growth in years. In all 3 years that I've planted these crops, there was difference in growth in any one of this, or it might be different in all three cases, but we will not be able to tell whether all 3 years are different in nature in terms of growth. The second thing is also we cannot say what genotype is different from each other, so we will be performing an ad hoc testing kind of thing to understand what group is performing better than what group. Then finally we will say interaction as well, interaction between genotype against years. So both, in all the three cases there are some differences, but hypothesis testing will not tell you what is the group that is differing, what is the year that is differing. It will simply say whether there is any statistical significant or not. In this case, it says yes, there is statistical significance. The other way to reject or accept null hypothesis is your calculated F statistic value, which is basically if your statistic value is greater than the critical value, then also we will reject the null hypothesis. This is another idea for accepting or rejecting null hypothesis. In that case also, we are going to reject the null hypothesis only. So basically, this here, my F statistic value is greater than the critical value in all three cases. Hence, I can go ahead and reject. But however, our primary focus should be on learning whether the p value is less than my alpha level or not. Looks like yes, it is. So in this case, we can go ahead and reject the null hypothesis blindly. It says all 3 years the growth was different. This is two-way ANOVA with replication. Let's move on to the next example. Two-way ANOVA without replication. We have students as one dimension and subjects as another dimension. Let me maximize this. Let me put it in dimensions. Students one dimension, subjects another dimension. Okay, we have two dimensions. Let's plot without the duplication ANOVA factor. Go to data pane, data analysis. Here I'll choose data ANOVA two factor without replication. I'll choose this. I'll supply this as my input range, and then I'll say labels are present. When I say labels, columns are there, and the alpha level is 0.05. The output range should be in the same sheet. It gives me the count, the summary for each and every student and for each and every subject. If I see the average varies a little, but I'm not sure if it is good enough for us to quantify whether they are statistically significant. So we will just use the same logic. The logic is two things we can validate. If my stress statistic value is greater than critical value, or if my p value is less than 0.05. In this case, we will reject the null hypothesis, or we will accept the null hypothesis. In this case, looks like both the cases are failing, so we will accept the null hypothesis. Now let me plot the null and alternate hypothesis. I'll simply denote it as H naught. Here, the first hypothesis is um, marks from different subjects are not different. Everyone are scoring same marks, same very similar marks in all three subjects. Then the second hypothesis, the second null hypothesis in this is all the students are scoring almost equally. The scores are also not changed. There is no poor student in this, there is no good student in this. Everyone are scoring very similar marks in these two cases. What is my alternate hypothesis? My alternate hypothesis is of A, marks from different subjects are different. All the students are not scoring equally. This is my second understanding. So this is my alternate hypothesis. In this case, what does it say? It says, it asks us to accept the null hypothesis. So hence we cannot say that the students are differently scoring marks in different subjects. No, all the students, almost all the students are scoring very similar marks in terms of the overall subjects as well as individual subjects. In each and every subject also there is no difference between each other. So this is one another understanding that we can take with the help of um, ANOVA, and then assume, not assume, we can statistically now say, see, there are no difference between any of the students. There are no differences between the neither of the students is scoring high marks or low marks in any of the subjects. That is all about ANOVA. You need to know. You need to know what is the type of ANOVA you need to do when you have one independent variable, when you have multiple independent variables, and how to interpret the output out of it. Let me show you quickly the same operation in Python as well. Mm, Hypothesis system. In Python or any other technology, we don't have to calculate anything manually. We just need, if we have the data at a group level, all we need to do is take the data and then plot it into type of analysis that you wanted to do. One way ANOVA, two way ANOVA, t test, z test, anything. Here it is all z test. Here we are performing ANOVA. If you see here, F test, as I told you, it is basically nothing but ANOVA only. In this case, I'm reading the data. I have two dimensions already, more than two dimensions for fertilizer, water, and yield. What I'm doing is I'm plotting the model and seeing what is the p-value. My p-value is 0.02, which is actually less than 0.05. In this case, we can go ahead and reject the null hypothesis. We are building a model here. This is the p-value. Look at the p-value. It is all less than 0.05, 0.05, less than 0.05, but here it is not less than 0.05. In this case, the interaction, the fertilizers and the water interaction is not having a good probability, but in all the other cases we have p-value less than 0.05, hence we can reject the null hypothesis. So that is how we can perform null hypothesis. And see here, the idea is, if the test statistic value is greater than or equal to the critical value that is generated, we can reject the null hypothesis. Or if the p-value is less than the alpha level, which is 0.05, in that case also we will reject the null hypothesis. This is the idea behind performing several types of statistical testing to achieve output which compares groups, means of several groups. If it is two groups, we will perform t-test or z-test. If it is more than two groups, then we will go with ANOVA, which is basically a product of f-test. That brings us to the end of this session. Now let me quickly recap what we have learned in this class. So we learned about what is analysis of variance. We learned about what is variance, how to calculate it manually, how to validate it. Once we generate variance, how to interpret it in the data set. Then we learned about two different types of ANOVA. One is one-way ANOVA, another one is two-way ANOVA. One-way ANOVA is basically a type of analysis of variance where if I have several groups under only one dimension, which is an independent variable. Whereas a two-way ANOVA can be done on two dimensions, where I have two independent variables and several groups within them. The way to interpret one-way ANOVA or two-way ANOVA is to evaluate the p-value with the alpha level. We generally possess an alpha level of 0.05, so we'll compare the p-value with the alpha level. If the p-value is less than the alpha level, then we'll go ahead and reject the null hypothesis and accept the alternate hypothesis. Now, p-value is simply nothing but the probability of occurrence of null hypothesis being true. That is all p-value is. So we need very minimal evidence to reject it. That is all the concept is. And the same applies for two-way ANOVA also. In two-way ANOVA, we learned about two-way ANOVA with replication and without replication, where the idea is when we can allow the same groups to take multiple tests, then it becomes two-way ANOVA with replication. Whereas you don't allow the groups or independent variables to participate in more than one test. You can conduct the experiment only once, but you can conduct it at a different groups in another dimension that we have. So basically, without replication becomes without duplicates, not allowing the user or the groups to group members of the group to take the test repetitively, just to avoid mishaps. So that brings us to the end of this class. Thank you so much for joining this class. Please don't forget to like, share, and subscribe to OdinSchool. Thank you one more time.